In this video lecture, we will be solving this problem network delay time, which is a LeetCode medium problem. In this problem, we're given a network of n nodes labeled from 1 to n, and we're also given times, which is a list of travel times, and each element in this times array is a directed edge from node ui to node vi, which has a travel time of wi, which says it takes wi times to reach the target node vi starting from the source node ui. And in this problem statement, we'll send a signal from a given node k, and we want to return the minimum time it takes for all the n nodes to receive the signal. If it is impossible for all the n nodes to receive the signal, then we return -1. Fine. So in the input, we'll be given a times array which contain triplets, n triplets, and an integer k, which represents the source node from which we send a signal. And in the output, we have to return an integer representing the minimum time it takes for all the n nodes to receive the signal. Let's see the constraints of the problem. We're given the length of the times array, and the integer k may go up to 100, while the length of the times array and the nodes are labeled from 1 to n, while the node u is never equal to node v, and the time which we take to travel from one node to another may go up to 100. And all the pairs, that is node pairs ui and vi, are unique. So let's better understand the problem statement using an example. So here we have an example which contains 4 nodes, and the source node is this second node, that is k is equals to 2, and at t is equals to 0, I send a signal from this source node to all other signals, and I want to find the minimum time it takes for the signal to reach the entire graph, if it is possible. So let's see whether the signal reaches all nodes or it doesn't. So you can see that in 1 second, so initially this is at 0 distance, this is at infinite distance, this is at infinite distance, and this is at infinite distance. So initially, so I can see that in 1 second I will reach the node number 1, and in 1 second I will reach the node number 3, and in 2 seconds, that is 1 plus 1, 2, I will reach the node number 4. And now we have all the times for each node, the time it takes to reach each node starting from the node number 2, which is the source node. And we can see that the minimum time it takes to reach all the nodes is 2 seconds, because in 2 seconds I'm sure that every node has received the signal, and hence the answer for this particular test case is 2. Fine, pretty simple. How would I solve this problem? Let's think about it. So we have a source node and we want to reach all the other nodes, and we have a directed graph which is weighted. You can see that part of the strategy to solve this problem is depth first search, which I will start from the source node, and this DFS will give me the minimum time for each node, minimum time for the signal to reach each node. Let's see how it will help us to solve the problem. So let's take this example to understand the solution of DFS better. So in this graph, we have 3 nodes named as k, a, and b, and we have directed edges. Then k is the starting node, so let's mark the distances of each node. So k is the source node, so the time it takes for the signal to reach the k node is 0, and initially the time for other nodes is, let's say, infinity. Why infinity? Because the signal hasn't arrived at these nodes yet, so it starts from this node. Then I traverse the adjacent edges for the node k, and I first traverse this edge, and along this edge, and I first traverse this edge. I call my DFS function here. So DFS is called at node number k, and while traversing the first adjacent edge or node, the time it takes to reach the node number b through this edge is 5, and we can see that 5 is less than infinity, so this time is lesser than the initial time that we have, and hence I will update the infinity by 5. Fine. So this is going to recursively call the DFS function for the node number B. So in the stack, so this is in the stack. So these calls are stored in the stack. So DFS K is in the stack, and now we have pushed the DFS B into the stack. So this is a call stack that I'm talking about. Then here I will again explore the adjacent edges for the node B, and I can see that the only adjacent edge which is directed from node B is this one. That means I can reach node number A from node number B, and the time it takes for the signal to go from node number B to node number A would be 5 plus 3, that is 8. That means the signal is reaching along this path, and the time it takes for the signal to reach to node A along this path is 8 units. And I can see that 8 units is less than the already existing time that we have for node A, which is infinity. So 8 is less than infinity, hence I will update this infinity with 8 because I want minimum time for each node. That's my target. So here I would have 8 here. Fine. And now I will have DFS A in the call stack. Then from this node I will explore the adjacent nodes, and I can see that B is the only adjacent node that I have towards which the edge is directed from node A. So I move to node B, and I see that the time it takes to node B from node A is 8 plus 2, that is 10, and 10 is greater than the time which we took to reach node B, and hence I will not update the time for this node. Fine. So, and this is the only node that I can explore from the node number A, and hence I remove this DFS call from the stack without updating the time for node B. Then I will go back to the DFS B, and here I have already explored the only edge which is directed from this node. Therefore I will remove this DFS call again from the stack. So now I have DFS K in the stack here, and I can see that another edge which I can explore from this node is this one, and hence I will call the function DFS A again. So this will be pushed into the stack, and then I will check if I can reach node number A from node number K. Then I will check the time which it takes to reach node number A right from node number K, and the time is 6 units, and I can see that 6 units are less than the already existing time that we have for node A, and hence I will update the time for node number A. So 8 is updated to 6. That means it is more optimal to reach node A along this path, that is directly go from K to A through this single edge rather than going from K to B then from B to A. So I will update the time 8 to 6. Then I can see that the DFS function will be called for this node because I'm updating the time for node number A. Here I can see that from node A I can explore this node B. This is the only node which I can explore because towards this node only the edge is directed from A. And let's check the time which it takes to reach the signal from A to B. You can see that the time is 6 plus 2, which is 8, and 8 is greater than 5. Therefore we will not update the timing for node number B because it is more optimal to reach node B along this edge. Fine. So we will not call the function for this node B, and I can see that node B is the only node which I can explore from node A. Therefore this function call is removed from the stack. Now I have only DFS K in the call stack, and I can see that I have explored all the adjacent nodes for this node. Therefore this function call will also be removed from the call stack, and I have obtained my minimum time for each node in the given network, which is 0, 6, 5, and minimum time for the signal to spread in this network will be maximum of the times for each node, that is maximum of 0, 6 and 5, which is 6, and 6 is the answer for this particular test. So that's how our algorithm is being executed over this input. Fine. So let's see the implementation for the approach which I explained here. So this is the implementation here, the adjacency list, which is used to store the graph or the network. And this is the network delay time function, which takes in the times. So this times array stores the triplets representing the edges and time it takes to travel that particular edge. N is the length of the times array and K represents the source node. Then I will iterate over the times array and I will construct my adjacency list or the graph. So in the graph, what I'm doing is, so the edge is directed from source to destination and it has a time as and this travel time is the time to travel from this source to this destination along this direct edge. Fine. Then for each node I'm sorting the edges in the increasing order of their travel time. Why I'm doing that? Because let's say in this case here for node number k I have two edges. The weight of the first edge is 5 and the weight of the second edge is 6. Then I'm sorting these edges according to these times or weights. Why? So that I can traverse the edge which has smaller weight so that I can first travel along the edge which has smaller weight. Why? Because it gives me more chances to reach the target node with minimum amount of time. For instance, to reach node number B through this path, like going from K to A, then from A to B, it takes 8 seconds, while to go from K to B, it takes only 5 seconds. Therefore, it is more optimal to first update the timing for node number B along this path by traversing this edge, so that the extra DFS function calls, which will be called from this node, are avoided. So if we already had the time 5 for this node, then I will never call the DFS function standing at this node for this adjacent node, because this 5 is less than 8. Otherwise, I will call this function DFS, first update the time from infinity to 8, then backtrack to the node K and traverse this edge and then update the time from 8 to 5. So it took me more DFS calls or function calls to arrive at the time 5 units. Therefore, it is more optimal to first sort the edges for each node in the increasing order of their weights or travel times. So that's the basic optimization which I am performing here. Then I will declare an array signal received at, which will be used to store the timing for each node when the signal arrived at that node. And I'm initializing this array with a very large number. So I'm comparing int max with the infinity. Then I'm calling this DFS function from this source node K. And this 0 represents the current time which we have for this source node. And for the source node, the current time is 0 because we are already standing at that node and we are sending the signal from that node. So it took 0 units to reach that. So here's the DFS function. So here's our DFS function which we called in the previous function, which takes in the signal received array, current node where we are standing. So initially it is the source node K and the current time. So initially it is 0 for the source node. So this is the base condition which I am checking. If the current time which I have for this current node is greater than the time which we already have in this signals array for that particular node, then that means it is of no use to update the time for that node. Therefore, I will return directly from here. Otherwise, I will update the timing for the current node to the current time. Then I will traverse the adjacent edges for the particular node, and then for the adjacent edges I will call the DFS function while updating the current time plus the travel time it takes for the edge from this current node to that neighboring node. So this travel time represent that, while the current time is the time to reach the current node from the source node. So this is how this depth first search function is working. Then after this depth first search function is executed, I will have my signal received at array prepared, which will store the minimum time for each node to receive the signal first. Then I will initialize an a variable answer to infinity or int to minimum value or int min so that I can extract the maximum value from the signal received array, because the maximum value represents the minimum time it took for the signal to reach all the nodes of the network, and hence that will be the answer. If the answer contains int max, that means there is at least one node which hasn't been visited. In that case, I'm returning -1, otherwise I'm returning the answer. Fine, let's discuss the time and space complexity for this implementation. So, since we are traversing all the adjacent edges, each particular node, in the worst case, we may have complete graph in which we have n multiplied by, in which we have edges of order n multiplied by n minus 1. In that case, the total number of paths would be of the order n factorial. And since I'm starting from the source node, I do not have to traverse that node and hence I will end up with n minus 1 factorial total paths which I had to traverse in case of a complete graph. So this is the worst case that I would have. Plus, I'm sorting the edges for each node, and let's say we have e edges for any typical node, that it would take me e log e time complexity for sorting those edges, and that is going to add e log e time complexity here. Hence, the overall time complexity becomes big O of n minus 1 factorial plus e log e, while the space complexity is big O of n plus e because of using my signal visited array. And so this is the auxiliary space which I am using because of the signals received array, while the stack space is also consumed, while the stack space would be big O of n, because in the worst case we may have n active DFS calls. Fine, so that's the time and space complexity. Let's move on to the implementation part. So this is the solution class which has two functions. So this is a DFS function which is used to perform the depth first search starting from the current node and the current time. Initially the current node is k, while the current time is 0, because I'm starting from source node k with the current time as 0. And this is the signals received at array, which will be used to store the timings for each node when the signal arrived there. Then this is the network delay time function which takes in the times array, the size of the times array and the source node, and returns the minimum time which is taken by the signal to spread in the given network. And this is the adjacency list which I globally declared to store my graph. So let's first build the adjacency list, iterating over the times array, take out the source node, destination node, travel time, and prepare the adjacency list. So there is a directed edge from source to destination with the given travel time. Then I'm sorting the edges for each node. Here I declare the array signal received at, which I initialize to a very large number. Then I call the function DFS, where I pass the array signal received at with the source node and the current time, which is 0. In this DFS function, I will first check if in the DFS function, this is the base condition where I'm checking if the current time is greater than or equals to the signal received at the timing which we already have for the current node. If it is the case, then there is no need to update the timings for the current node, and hence I return right from here. Otherwise, I update the current time for the current node in the given array, and I traverse the adjacent edges for the current node. And for the adjacent edges, I will recursively call the same DFS function while passing in the time to reach those nodes. Fine. So after this function is executed, I will initialize my answer array to a very small number, and I will extract the largest integer which I have in this signal received at array, because that integer will represent the minimum time for the signal to spread in the network. And here I'm checking if the answer is int max. That means there is at least one node which is unreachable. In that case, I'm returning -1, otherwise I'm returning answer. Fine. So this is the implementation in C++. I've attached the implementations in other languages in the description, so make sure to check it out. So that's all for this video. If you like the video, then hit the like button and make sure to subscribe to my YouTube channel and give your feedback in the comments below. So I've attached the link to the entire playlist of the medium lead code problems in the description. So make sure to check it out, and I will see you in the next video.